Modern backend server infrastructure operates under severe constraints. These systems must handle millions of concurrent data packets, route information instantly, and do it all without crashing the physical hardware hosting them. This scatterplot graphs the performance landscape of major programming languages. The horizontal axis tracks how much memory a program consumes, while the vertical axis tracks how fast the code actually executes. Interpreted languages like Python and JavaScript typically land down here. They translate code at runtime, which limits their execution speed, and they carry a significant memory footprint. Language ecosystems like Java solve the speed problem. Their code executes extremely fast, but they still consume massive amounts of memory to run. Natively compiled languages like C++ and Rust sit in the ideal quadrant. They consume very little memory and execute rapidly. But writing and compiling them can slow down developer iteration. Go lands right here. It achieves execution speeds and low memory footprints similar to C++, while maintaining the rapid, near-instant compilation speeds of much slower languages. It achieved this precise positioning by actively rejecting the standard software engineering paradigms used to build almost every other popular language. To understand Go's architectural advantages, transitioning developers have to unlearn three things: virtual machines, object-oriented inheritance, and exception-based error handling. Interpreted execution involves a program reading human-readable code and translating it into machine instructions while the software is actively running. This live translation inherently bottlenecks execution speed. Native compilation solves this by forcing the computer to translate everything into binary machine code before the program ever runs. This diagram compares the architectural pipelines. Python runs through an interpreter on the left. Java and C# occupy a middle ground. Their source code compiles into an intermediate bytecode, which is then executed inside a virtual machine. That virtual machine comes with a heavy cost. It requires a massive, constantly running environment to manage memory and clean up unused data via a garbage collector. This eats up server memory even when the program is completely idle. Go bypasses the virtual machine. It compiles directly into a single, standalone native binary of ones and zeros, exactly like C or Rust. Historically, the trade-off of native compilation was memory management. The developer had to manually allocate and free up space in the system's RAM, which is notoriously prone to errors and memory leaks. Go solves this with a unique compromise. It embeds a miniaturized runtime directly inside every single compiled binary. This embedded chunk of code automatically handles garbage collection natively. You get automated memory management without the massive footprint of a JVM, all packed into a single executable file that requires zero external dependencies to deploy on a server. Traditional object-oriented programming relies on explicit class inheritance to model complex data. Look at this standard class hierarchy. A parent-employee class defines core logic, which is then inherited by full-time and contractor subclasses. Deep hierarchies create tight coupling. If you change a method in the parent class, every child class downstream is forced to adapt, making rigid structures difficult to refactor over time. Go abandons classes entirely. Instead, it uses structs, simple, independent collections of key-value pairs that share no hierarchical parent. To create shared behavior, Go relies on interfaces. An interface is just a blueprint containing required method signatures, like a shape interface that requires an area method. In traditional languages, a class must explicitly type out that it fulfills an interface using specific keywords. The object must be aware of the interface it serves. Instead, Go simply opts for implicit fulfillment. This employee interface requires a getSalary method. Down below, our full-time and contractor structs don't declare any relationship to that interface. But because both structs possess the exact getSalary method required, the compiler automatically links them. This allows you to piece together modular components organically. You can define small, highly specific interfaces to group data long after the underlying structs were originally written. JavaScript, Python, and Java rely heavily on the try-catch block to handle errors. The standard workflow involves wrapping multiple, potentially dangerous asynchronous operations, like these network requests, inside a single try block. This creates severe scoping bottlenecks. Any variables declared inside that try block are trapped there. They are entirely inaccessible to the code running further down the page. To keep data accessible, developers are forced to write deeply nested logic trees, or declare empty variables outside the block to catch the state leaking from inside. A broad catch block also obscures exactly which function triggered the failure, hiding the true source of the error. Go discards exceptions. It treats errors simply as standard values, the same way it treats strings or integers. Functions in Go can return multiple values simultaneously. When you execute a dangerous function, it cleanly passes back both the requested data and a potential error value. This code relies on the guard clause pattern. Immediately after a function runs, you check if the error value exists. If it does, you handle it and return early. The variables are perfectly scoped to the rest of the function. The code bypasses scoping traps and flows cleanly, straight down the page. Treating errors as explicit values forces developers to handle failures right at the source, creating highly predictable logic without hidden nested execution trees. Go commands this optimal intersection of high performance and low memory by stripping away abstraction. It avoids JVM bloat by embedding a garbage collector directly into a native binary. It drops rigid hierarchies for implicit interfaces and replaces try-catch scopes with linear guard clauses. These architectural choices prioritize maintainability, readability, and hardware efficiency over developer shorthand and syntactical magic. For teams building massive concurrent backend infrastructure, minimizing hidden state and shutting runtime dependencies is the exact architectural formula required to deploy resilient systems.